Okay, so Caltech recently released their early action decisions, so we're on their website. Future scientists and researchers, consider this hypothetical scenario. Open your vector calc textbook for the first time. Well, let us open our vector calc textbook and see what happens. So we're going to skip this problem for now. It's tedious. We'll do problem number 4. So for problem number 4, we want to prove that n choose k plus n choose k minus 1 is n plus 1 choose k. We're going to do this two ways. One of them is going to be algebraic. So for the algebraic proof, we just use the definition of n choose k, n factorial, k factorial, minus k factorial. And similarly, we expand for this, n minus k plus 1 factorial. And then for the right-hand side, we do the same. N minus k plus 1 factorial. So what we're going to do is we're going to multiply both sides by this denominator here. And so for this term, the k factorials will cancel, but this will add one more term. So we'll get n factorial, n minus k plus 1 plus, and then similarly, this will cancel, but this will add a k term, n factorial times k, and then this will just become n plus 1 factorial. So from here, we can factor out the n factorial. So this will be n minus k plus 1, which is just n plus 1 factorial. So these two are the same. Another way we can do this is with a combinatorial proof. And the way that works is that we suppose that this side is counting the same thing as this side. As in, we have some sort of, we imagine that these are processes to count some system. And if they're counting the same thing, then they must be equal. So to see that in action, we're going to look at the right-hand side. And we see that the right-hand side, because it's simpler, right? This is like one term versus two terms. Right-hand side, we can imagine that we're picking k people from, n plus 1 people. And, by this is basically a definition. This is like, there's n plus 1 choose k ways to do that. If we're picking k people from n plus 1 people, we're choosing k people, we could say. But now let's look at the left-hand side. We have some sort of special person. For the special person, that we care about. For the special person, we have two cases. One is that we pick them. In that case, we've already picked a person. We need to select k minus people from the remaining n. So that's going to be n choose k minus 1. The other case is we don't pick them, in which case we still need to pick k people, and we have n minus 1 remaining since we started off with n plus 1 people. So we have n people remaining. It's going to be n choose k. So since these two situations are disjoint, they don't overlap because, either we pick the special person or we don't. It can't possibly, there can't be a case that's in both of these scenarios. And it also covers all the cases because either we pick them or we don't, right? So since they're independent and they cover the entire scenario, the total number of ways to pick them is just going to be the addition of these. And so since the LHS is counting the same thing as the right-hand side, that means they're equal. And that completes the proof. Okay, so first problem wasn't too bad. I can just, okay, actually it's probably faster just open a new document. So, okay, next problem, problem 5. Use a previous problem to prove the binomial theorem by induction. Okay, so problem 5. Prove the binomial theorem. Okay, so they said it's inductive, so we're gonna do an inductive sketch. So base case is when n equals 0. Remember, we're trying to compute the binomial theorem gives us a way to expand stuff of the form x plus y to the power n. So our base case is, very simple, n equals 0. In that case, x plus y to the 0 equals 1, which is certainly, the binomial theorem tells us it should be 0 choose 0 times x to the 0 y to the 0. Certainly 1, so that checks out. And now we look at our inductive case, or the meat of the proof. So we assume it works for n, prove it works for n plus 1. So we look at x plus y to the n plus 1, and that is of course equal to x plus y times x plus y to the n. Okay, so we're gonna sort of do induction on, I guess, this, right? We can use our inductive hypothesis on this part, and then just add on this. So one way to look at it is that we look at some term. So we pick some term x to the k, y to the n plus 1 minus k, right? This is because the powers of these need to add up to n plus 1. So we look at this term, and we want to find the coefficient of this, right? So so basically one view of polynomial multiplication is, instead of thinking of it as like multiplying, think about it as choosing terms from the polynomial. So if I want to multiply like something like this out or whatever, then like one way to think about it is I'm choosing a 1 and then I'm like picking a 3x, and that gives me a 3x. So in this case, we have two cases here too, right? Similarly to our previous one. Either we pick x from the x plus y, this term here, or we don't. If we do, then there are n choose k minus 1 ways to make x to the k, because we picked an x from here, and then now we have n x's here, and we need to get it to k here, right? So in that case, we need to pick from these n x's in the sequence here, we need to pick k minus 1. If we don't, then there are n choose k ways, because we need to pick our k x's from here. So in that case, the coefficient of this must be n choose k plus n k minus 1, and which by our previous theorem is just going to n plus 1 choose k. So that means that the coefficient of this term here is going to be n plus 1 choose k, x to the k, y to the n plus 1 minus k. And that completes the proof. Oops. Okay. So problem 5, use the previous, So problem 6, setting j equals k minus 1, rewrite the generating rule and use it to prove a formula. Okay. So recall that our generating rule is n choose k plus n choose k minus 1 is n plus 1 choose k. So we're going to set j equals k minus 1, which means that k is going to be j plus 1. So we can rewrite this as n choose j plus 1 plus n choose j equals n plus 1 choose j plus 1. And then subtracting this from both sides, we get n choose j is equal to n plus 1 j plus 1 minus n choose j plus 1. And that agrees with their generating rule. So now I'm going to use this theorem and apply it to this sum from n equals 1 to m of n choose j. So just expanding using this is the sum from n equals 1 to m of n plus 1 j plus 1 minus n j plus 1. And we notice since this chooses the same, and as increases, this is sort of going to telescope. We can see that by just writing out terms. So when n equals 1, we will get something like 2j plus 1 minus 1j plus 1, 1 choose j plus 1, and when n equals 2, we'll get 3j plus 1 minus 2 choose j plus 1, and then when n equals 4, or 3, sorry, we'll get 4j plus 1 minus 3j plus 1. And we see that this cancels with this cancels with this, and it's gonna like keep on canceling here. And so finally, if we add all this up, we'll get something that looks like, yeah, the final term here is gonna be when it's m. So this final term is gonna be m plus 1 j plus 1 minus m j plus 1. So this is gonna be like the survivor term, and so is this. So this final sum is going to equal something like m plus 1 j plus 1 minus 1 j plus 1. So unless j is 0 here, this is going to be 1, because 1 choose 1 is 1. But if j is greater than 0, if j is like 1, then 1 choose 2 is sort of ill-defined, right? Like you can't pick two things from 1. So this is going to be 0. And if we assume j is greater than 0, then this is just going to be something like m plus 1 j plus 1. Which we're going to keep in mind. And then finally, actually we could prove this combinatorially. Yeah, okay, let's see what it would look like combinatorially. So let's do it combinatorially. We have n choose k, and we want to write it as the sum of n minus 1 k minus 1 plus n minus 2 k minus 1 plus, and so on, till we get n minus k, oops, n minus k minus 1, choose k minus 1. Because this is just k minus, this is just the like last positive. This is the smallest term. So in this case, the left hand side is just going to be, we're choosing k people from n. The right hand side is more interesting. So the right hand side, we're basically, imagine we're ranking these people, rank the people. Then we care about the lowest rank. So we're ranking these people and we're caring about the lowest rank when we pick k people. In that case, we're going to look at cases on R. Where a case R means that we have exactly one person with rank R. And I guess the exactly one person doesn't really matter, but the important thing is that this R is the lowest rank. Like out of all the people we picked, all the k people we picked, the lowest person has rank R. Oh, and by the way, we're ranking from left to, like, it doesn't really matter, but like if we imagine like there's a person here, so on, then this guy's going to be a 1, this guy's going to be a 2, and then this guy's going to be in or something. So we picked exactly one person with rank R. That means that we can't pick anyone. Okay, so let's draw this out. I guess, yeah, we'll draw this out. So this is like person 1, person 2, person 3. This is person R, rank R, R plus 1, so on until we get to n people. So we picked this person with rank R plus 1. We can't pick any people here because this has to be the lowest rank. So we can't pick any people with a lower rank. So we have to pick the remaining. So we have to pick k minus 1 people because we need to pick k people total, and we've already picked a person. So there's n minus r people left since we've eliminated these r people, and then we need to pick k minus 1. So there's that many ways to do it. N minus 1 choose k minus 1. R can vary from R to The lowest rank possible is 1. The highest rank possible is not in, because the lowest rank can't be in, because if our lowest rank is in, that implies we need to pick, k minus 1 more people from, and there's no other ranks, so we've ran out of people. So the lowest the highest r can possibly be is r minus k n minus k minus 1. So in this case, since each of these cases are independent, because they're characterized by this person with the lowest rank, they're independent and they cover all the possibilities, which means the total number of possibilities has to be just starting from each r. So if r is 1, then it's n minus 1 k minus 1. If r is 2, then n minus 2 k minus 1, and so on, until we get to n minus k minus 1, choose k minus 1. And since we're counting the same thing, we're just choosing k people from n. That means that the left hand side is equal to the right hand side, and that completes the proof. So let's just refresh our memories for what we proved. We proved that n equals 1 to m of n choose j is going to be m plus 1 j plus 1. Okay, so for the final problem, we use the previous problem to derive a formula for the sum of the first 4 m fourth powers. So we want to find a formula for something that looks like this. This is a very typical sort of sum. Like, for example, if m is like, this just looks like 1 to the 4th plus 2 to the 4th plus 3 to the 4th, and so on until m to the 4th. So in this case, we need some way to, we have like a formula like this. So we have this in mind, and we want to somehow transform this into this. So we need to write into the 4 as a function of these, like, look, this summation term here, like, here is the same as here, right? So this summation term is the same. We need to write into the 4th as some way of n choose j, right? And so if we just think about like what these look like n choose 1 looks like n, or I guess we should start with, n choose 1 looks like n choose 2, I mean, not looks like, but is n choose 2 is n times n minus 1 over 2, and n choose 3 is, something. But the point is that this is like n squared, O of n squared. So whenever we have into the j, that's going to be a polynomial of degree into the j. 2. Okay, so that means that we need to, if we want to write this as sort of a combination of these, then that means that it needs to be, we need to start at 4, right? N choose 4. So we're going to have some mystery coefficient times n choose 4 plus some other mystery coefficient times n choose 3, and so on until we have some mystery coefficient times n choose 1. Okay. So to do this, we're going to do a combinatorial proof. And we're going to, so we're going to do a combinatorial proof. Not even a proof, because we're discovering the right-hand side as we go. We're going to think of this as the number of ways to generate a length-4 strain with n characters. Because into the 4, like, you can imagine, like, we have this length-4 strain. If we have n possibilities here, and n possibilities here, and n possibilities here, and n possibilities 4, then this is into the 4 possibilities for this entire string, right? So in that case, what's the right-hand side gonna look like? And for the right-hand side, we imagine that instead of just generating this string outright, we care about the number of distinct characters. So we're going to split it into cases. For example, if we have only one distinct character, then there's only one way to if we only have like, let's say our character is A, right? Then there's only one way to generate a string. It would just look like A. And so 1 is our coefficient here, and we have since we have n possible characters, we have n choose 1 ways to get like one distinct character times one possible way to generate. Like, for example, like we would have B maybe, and we'd have like, you know, up until like maybe E if n is like 5. A, B, C, A, B, C, D. Yeah, okay. So we have n choose 1 ways to get one distinct character, and if for each distinct character, there's only one string you can generate. So this is going to be the total number of ways, the total number of strings we could generate with n characters and one distinct character for the string. For a case of 2, then we can use 2 possible characters. And in this case, how many? So this is basically answering. First of all our like characters are symmetric. Like, you can imagine that we picked AB or AE or BC or whatever. It doesn't really matter. So we're just gonna, because they're all symmetric, so we're gonna call it like 0, 1. The question is, how many strings of length 4? How many binary strings of length 4 can we generate? But importantly, it's not just all possible binary strings, right? Because that would just be 2 to the 4 is 16. It has to be, not only do we have 2 distinct characters, but they have to be exactly 2 distinct, right? So this doesn't work because this we already counted in the one character case, right? So this doesn't work, and a string that looks like 1, 1, 1, 1 also doesn't work. So out of our 2 to the 4 possibilities, we actually, 2 of them actually don't work. So this is going to be 14 in actuality. And so that means that this contributes 14 strings per 2 characters times n choose 2 ways to get 2 distinct characters from n characters. For 3, just keep going, I guess. And for the case of 3, this sort of starts getting tedious, so we need to sort of generalize it. We're not going to do 3 using brute force. So let's look at a case R, say, or case K, I guess, is more standard. So we want to generate a length in string with K, or a length 4 string, K distinct characters. The string has to have K distinct characters. It can't have any less and it can't have any more. So exactly. Our characters are distinguishable because we can tell them apart, and so is our characters are distinguishable. And so basically we're gonna the way we're gonna think about how to count this is we're going to think about it in terms of I think the analogy is boxes and balls in boxes, putting balls into boxes or something of that nature. The idea is that our boxes are going to be the boxes are going to be the K distinct characters. So we're going to have K boxes. Each one is like a character, right? So this might be A, this might be B, and so on. Our boxes are going to be all these characters. And then our balls are going to be the 4 indexes, right? So we could put the 0th index into like here. That would mean we have like A. The 2 index into here. So that would mean we have like 0, 1, 2. We have like C here. I guess it's an E. And so on. So this might be B or something. And in this case, our mapping from balls to boxes first has to be surjective. Because it has to hit all of the characters here, right? Second, it has to be the boxes are distinct because the boxes are the characters, and so are the balls. The balls are distinct because they're the indexes, and we can tell them apart. So it's distinct, and it's distinct. So we have a surjective mapping, and we're going from distinct to distinct. In this case, we can just apply the 12-fold path, which is the 12-fold way is a standard way to do counting problems, and that tells us that basically we're gonna look at the Stirling numbers. I think this is the Stirling of the second kind. There's also Stirling numbers of the first kind, but I'm not quite familiar with those. So for Stirling numbers of the second kind, that means for S of n k, that means we're trying to form n people, and we're putting them into k groups, and exactly k groups. So we can't have like, so if we have these people here, we're trying to put them into 2 groups. We could have something like this, but we could not have something like this because that would be 1 group. So we could have like this and then this. We could have like this and then this guy by himself, or there's some variations there. But we can't do this, and we can't do like this because that'd be too many, and then yeah. So exactly k groups. In people, exactly k groups. So if we think about our 4 indexes, so n is 4 in this case, and we pick k characters and we put our 4 indexes into the k character groups, that works. But then we also need to multiply by k factorial because the characters are so this is like this, when I say groups, like this doesn't, the people you group matter, but the group order sort of doesn't matter, if that makes any sense. Like if this is a person A, this is a person B, this is a person C, then we might assign person 1 to person A to group 1, person B to group 2, and person C to group 1. Or we could assign person A to group 2, person B to group 1, and person C. So we have these 2 group assignments, right? These are the same group, obviously, because that just means, it, like in terms of a pictogram, it just means that these 2 are together and this person is by themselves. So these 2 are counted as the same thing. This is just like, these are identical. So in this case, while like this would be like S of 3, 2, we're putting 3 people into 2 groups. That would count like, but we have, when we have 2 groups, like we might imagine there's like a group 1 and a group 2, but that would count this as the same because we only care about the group assignments. In this case, we do actually care about what group these guys are assigned to. Like we care that these are in the same group, but we also care that they're assigned to group 1 or group 2 because this would be character A or character B. So we have to multiply by k factorial because the group order matters. So that will account for the fact that these are sort of like, we can imagine that like we have like an abstraction of groups, and then when we do the k factorial, we're basically just assigning our characters to our numerical groups, right? Anyways, so let's go back to our original problem. We were trying to write into the fourth as something times n choose 4 plus something times n choose 3, so on until something times n choose 1. Well, I'm saying that for a case n choose k, the number of strings is actually Stirling number of 4 times k factorial. So into the fourth is n choose 4 times there's only one way to put 4 people into a group of 4. You just put them all in the same group. So this is going to be 4 factorial plus n choose 3. And the number of ways to put 4 people into 3 groups is going to be I think actually so there are basically 2 cases here. Either actually no, there are not 2 cases. You need to have group sizes of 2 and 1. So or sorry, 2 and 2, I suppose. Group size of 2 and 2. So, or 2 and 2, or no, sorry, 2. Yeah, sorry. I got you didn't have 3 groups, which means you'd have groups like 2, 1, and 1. Yeah, this is the only possible group structure. You have 2 people in one group, 1 person in their own group, and then another person in their own group. So in this case, if you pick the 2 people here, then the groups here just form themselves basically. So 4 choose 2 is 6. So the number of ways to put 4 people into 3 groups is going to be 6. So 6 times 3 factorial. The number of ways to put 4 people into 2 groups. We can do some clever logic here. So as you can imagine, we either assign each person to like we have group A and group B. We assign each person to group A or group B. So naively that would just be 4 to the 2. 2 to the 4. I have that backwards because we're doing 4 binary situations. But we have to subtract the fact that we can't have a group of all A's and we can't have a group of all B's. So we minus 2 here. And then we have to divide by 2 because A and B are interchangeable. Because, if we have the same, if we have the same assignment here, a 2, 1, 2 is the same as 1, 2, 1 in terms of Stirling numbers. So this is going to be 14 over 2 is 7. And, in general for Stirling number of in people into 2 groups, that's going to look like minus 2, which is going to be 2 to the n minus 1 minus 1. So yeah, slight tangent, but in this particular case, that means that this is going to be 7 times 2. And then finally for n choose 1, the number of ways to put 4 people into one group is you just put them all in the same group. Sorry, for 4 people into 4 groups, the way you do that is just you put them in each of their own groups, right? And for 4 people into one group, the way you do that is you just put everyone into one group. Okay, so we now have n to the 4 as a linear combination of the choosing. And so again, remember that we have this theorem, or this identity, I guess, that this is n plus 1 j plus 1. Okay, so finally we're just gonna apply this. So okay, we can just do this here, I guess. So sum of n equals 1 to m of n to the 4, which is going to be the sum of n equals 1 to m of, the 24 here. So the 24 comes from 4 factorial is 24. So 1 to m of n choose 4 plus 3 factorial is 6 times 6 is 36. N choose 3 plus this is 14, so n choose 2, and then plus 1. And finally, using our identity here, we can turn each of these into 24, m plus 1, choose 5, plus 36, m plus 1, choose 4, plus 14, m plus 1, choose 3, plus 1, m plus 1, choose 2. And that's our final answer. So this is not quite an explicit formula for, recall that, what that gave us basically is that gave us an explicit, a formula for something like this, like 1 to the 4th plus 2 to the 4th plus 3 to the 4th to m to the 4th. And so this is in terms of m, as you can see. So while it's not quite an explicit formula yet, it pretty much is. We could, if we wanted to turn this into a regular polynomial, we could just expand all of these and then compute the polynomial. But this is good enough for our purposes. And so to conclude with, this Caltech, vector calc homework, very interesting problem, sort of unusual. We started off with some sort of trivial algebraic identities here. We went on to do some more extensions. Binomial theorem follows from that. We do some more combinatorial proofs, prove some sort of telescoping identity. But finally, we apply that to this algebraic problem, which at first glance has nothing to do with combinatorics at all. We're just trying to find the sum of this, and we can turn that algebraic problem into sort of a combinatorial thing where we imagine generating a strain, and that turns into Stirling numbers somehow. And at the end of it all, we have this 1 to the 4th plus 2 to the 4th plus 3 to the 4th plus m to the 4th. We have this identity that we got from imagining strings and combinatorics. So I thought this problem was very interesting.